It is time for the sequel to the Problem 10 hint video. And when last we spoke, I had just made the argument that I could solve this problem by picking an origin at the base of the trajectory, setting up a coordinate system that was parallel to the ground, and with y going in the up-down direction. And then in this coordinate system, the answer to our problem is the hypotenuse of this triangle here, which has a little interior angle of theta. And then the projectile is launched relative to the horizontal here with an angle of theta plus phi. Okay, well, given all that, let's write down some kinematic equations. By virtue of my choice of origin, I can go ahead and simplify my x-coordinate equation a little bit by saying that x0 is going to be 0, just from my choice of origin. And then my actual x distance up here is the point x, y. I'm going to go ahead and short circuit the problem a bit by saying that that is also here equal to d cos theta, which is just this x-coordinate. So I go ahead and I get d cos theta is equal to v0 times the cosine of the full velocity trajectory, and that's the theta plus phi, all times the time. And then following the standard pattern for this kind of problem, what I'm going to do is I'm going to solve for the time by dividing the v0 cos theta under, and we'll get d cos theta over v0 cos theta plus phi. Okay, now we actually want to return to the y equation, and so I go ahead and get kind of a similar pattern. So y is equal to y0 plus v0 yt minus 1/2 gt squared, where the minus sign comes from the fact that gravity is down opposite the direction of our y-coordinate here. Now I can again get y0 equal to 0 by my choice of coordinate system, and then y is just going to be d sine theta. And then I'm going to go ahead and plug in that v0 y is v0 sine of theta plus phi times the time, which I've already solved for over here, so I can say that that is d cos theta all divided by v0 cos theta plus phi. And you'll notice that these terms are going to cancel, and this will get a tangent, just like in the ninja problem. So that's just the first term of this equation. And then I'm going to go ahead and try to sneak in 1/2 g times t squared here, which is going to be d cos theta over v0 cos theta plus phi, and this whole thing here is squared. Okay, well, at this point I see a lot of good simplification that can happen. Just for the length of it, I'm going to just recopy this thing down here, carry out this squaring, and go ahead and cancel these v0s and turn this into a slightly more compact term. So I'm going to get d sine theta on one side of the equation. That's my y-like coordinate. Then over here, cancel those v0s, and I end up with d times the cosine of theta times the tangent of the sum of the angles, theta plus phi. And I'm going to subtract from that my gravity acceleration term, 1/2 g, d squared cos squared theta all over v0 squared cos squared theta plus phi. We have to take this whole mess and isolate for d. That's what the problem wants, right up here. How far up the ramp d does the ball land? I kind of picked it this way so this could all work out nicely. And I use nicely with air quotes that you can't see right here. But one thing to note is that d appears in every one of these terms twice here. So I can go ahead and factor out a d and cancel it from each of these terms, d, and then this d squared gets canceled out. Well, then I've got one term with a d and a bunch of things without, so I'm going to push this to the other side. It's going to switch signs and pull the sign over here, and I'll end up with an expression that looks like g over 2. Oh, I put the d in front to make this a little easier to see. Factor it out. That's the g over 2 term. Then I've got cos mesotrig, cos squared theta, over v naught squared, it's totally squared, times cos squared of theta plus phi. And that mess is equal to cos theta tangent of theta plus phi. And then we have the sine theta term, which comes over here and becomes minus sine theta. So this is a sum, and I'm going to multiply that by the inverse of this term in order to isolate the d. So I get d is equal to, and this just flips the whole thing, so 2v naught squared over g. That's good. This whole expression looks like a height to me, or a distance, and then the rest is just numbers, or numerical factors. So then we get cos squared of theta plus phi all over cos squared theta, one numerical factor, and the other numerical factor, cos of theta times tangent of theta plus phi minus sine theta. Now it's all over but the calculator screaming. So we say that that's 2 times, sub in the value up here, 7.71 meters per second. 7.71 meters per second, quantity squared, all over 9.81 meters per second squared. Theta plus phi, I can go ahead and say that theta plus phi is equal to 1.31 radians. So then we can go ahead and drag this down here and get that that's cos squared of 1.31 over cos squared of theta, which is 0.62. Okay, that's clean enough. Then we take that and we go times cos of 0.62 tangent of 1.31 minus the sine of 0.62. And plugging this into my calculator, I pull out a surprisingly round number, which is 3.00 meters. Amazing. And that's all we wanted.